Yeah, thank you very much for the kind introduction. I'm very happy to be here and to be the guy between you and lunch. As already said, my name is Daniel Wenz, and I'm here today on behalf of the Xenon collaboration. And I would like to show you not only the status of Xenon Anton, but we're also happy to present you the first results of Xenon Anton, which you also see here in this nice picture. So the Xenon collaboration is distributed worldwide. We have like 27 institutes and we're about 170 members. So this is one of our recent collaboration meeting images. And we learned already today by other talks about dark side, but also about cosinos, that in direct detection experiments, low backgrounds is key for these kind of experiments. And so what I want to do before showing results is giving you an impression what new features we have in Xenon Anton compared to Xenon Anton to improve on the overall quality. 2 points where I don't have time to go deep into it is our new software which we're using and our triggerless data acquisition approach, and also about the cleanliness and radio purity procedure. So if you have questions, just find me during lunch. So let's start with the TPC. We had already yesterday by Kimberly a very nice talk how this works, but maybe just a little recap. So basically what you build is a cylinder, and you have on the top and the bottom part you have photosensors, and you fill this cylinder with some medium. In our case it's liquid xenon. And so what you're doing, you're observing with your photosensors this medium, and when a particle enters this detector, you're producing a recall and you're producing a first scintillation signal, which we call S1. And then you also create free charge carriers, which you can drift upwards due to a drift field. So we have electrodes in our detector, and up here we have an interface between liquid and gas. So you extract the electrons into the gas, you produce a second scintillation signal, proportional to the number of electrons, the so-called S2. So why so complicated? Basically, we're doing it for two good reasons. The first reason is that you can discriminate particle types. So if you have electronic recalls, so beta gammas, but also axions, they preferably interact here with the electrons. And when you compare this to nuclear recalls you get from neutral particles like neutrons or neutrinos, but also WIMPs, you interact primarily with the nucleus and producing a nuclear recall, and so you get different S2 sizes. And basically, if you look at S2 versus S1, you can see your electronic recalls up here and your nuclear recalls down here. So you have particle discrimination. The other thing is that you can fiducialize your volume, which is shown here actually already for Xenon Anton. So what you basically do, you're not looking into the entire volume for your dark matter signals. You're just define an inner virtual volume in which you look for your signals. So there's blue regions, in our case it's about 4.4 tons, and everything on the outside of the detectors, which is mainly background, basically you discard. So about the new systems, as I said already, purity is key, and here we have two nice systems. So one is located down here, which is taking care of the xenon purity. And so one important aspect is now if you drift these electrons is that you need a very pure medium, because if you have electronegative impurities like oxygen or water, they basically catch away your electrons. And so to get a detectable signal, you need to purify your xenon. And in Xenon Anton, we have now this liquid purification system, and we are purifying about 2 liters of liquid xenon per minute, so roughly 18 hours for the entire volume. And if you compare this from 1 ton to Anton, in 1 ton we had a drift length over the entire TPC of about 0.7 milliseconds, and the electron lifetime was in the same order. So you get, you're left with 30% of electrons at the surface. In Anton we have unfortunately a slightly lower field, but also larger detector, so the drift time is longer, but also our electron lifetime is very excellent in Xenon Anton. And through SR0, the average is about 15 milliseconds, so we have a survival probability of about 90%. The other thing is that to reduce the backgrounds, one of the most dominant backgrounds is radon. And so what we have located up here in our service building is a radon distillation column, so this is the distillation column. In addition, also some magnetic piston pumps. And this helps us to reduce this radon 222 content quite a lot. So if you compare, for example, here in this plot, the content measured in Xenon Anton, which is about 1.77 millibecquerel kilogram, to the one measured in Xenon Anton, which was 30 milligram per kilogram, you see that we have quite this huge reduction factor simply by basically taking the xenon here, vaporizing it, so the radon stays here, and then you basically recondense it and bring it back. And if you're more interested, I also always link the papers to these subsystems. So then we have also, in addition, the new xenon antineutron vetor. This is something where we have a heavy contribution from Wenz and where I'm also working on for the most part. And this is this detector shown here. So this is an octagonal shaped white shiny structure where you have PMT surrounding the cryostat, watching this TPC cryostat. And what you basically want to do is that if you have neutrons emitting from your detector materials, producing a nuclear recoil in your detector, so something which looks like a dark matter signal, going out of the detector, you want to tag these neutrons. And you do this by basically capturing on water, producing a gamma, and then in the second processes then Cherenkov radiation. And so for the tagging efficiency, we estimated now a value of about 68% for the neutron vetor. At later stages of xenon anton, we want to even dope this with gadolinium, so you increase basically the amount of energy emitted when you capture a neutron to 8 MeV, and then based on our simulations, we think that we can achieve tagging efficiencies even up to 90%. So these are the new systems, but since I want to present you also today some results, I also should show you how we calibrate the detector and to prove to you that we really understand our backgrounds and what you usually do. You have different calibration sources shown in this nice t-shirt plot basically here. So you have the S2 versus the S1 signal I was talking before, and you have different calibration sources, and they always appear as ellipse-like structures in these plots. So here you have argon, here we have krypton, then you have xenon, and then here up here you have higher energetic background material, gamma lines, and so on. And the nice thing about argon, krypton, and also these xenon lines is that they are uniformly distributed in the detector because they are just diluted in the liquid xenon, so you get a uniform calibration. And so you basically estimate how much charge do you see per unit energy and how much light you see. You put basically on this line. Here you have these high energetic krypton xenon, then you have the even higher material lines, and here you have the low 2.8 keV argon line, and then you basically get your energy response. What you can also do with this krypton is basically do bi-weekly calibration to monitor stability of your detector, the response stability, but also the drift field of your detector. Then the other two things you need to know, okay, now we know all the corrections we need to apply to our detector, but you should also be aware of the electronic recoil response and the nuclear recoil response of your detector. And for this, for the electronic recoil response, we're using radon 220, and this is shown here again, S2 versus S1. In blue you see the data, and in gray you see the best fit. And the nice thing about this is it's a beta emitter, so it has a flat spectrum. It's very excellent to validate cuts and detector thresholds. And in addition, I said this already, we have the argon 37, which provides you this very low energetic line at 2.8 keV. And so this is also a nice contribution here from Wenz, where you can also go to the poster by Christopher Hitz. And when you fit now the two sources together, this is what we did. You get our electronic recoil response model, basically. What you also see down here in counts as a function of energy. So for the nuclear recoil response, this is again something where I was more involved, is what we used here is a neutron source, an americium beryllium source you might be familiar with, and it emits, the nice thing about that, it emits a gamma and also a neutron at the very same time. And so since we have now two detectors, what you can do, you can observe the gamma basically in the neutron veto and the nuclear recoil event in the TPC. You might get tight coincidence between the two, and then you basically reduct your background, which you see a lot here, by just applying this coincidence, and you get the nice calibration spectrum, which is very beautiful to calibrate the response. And then there's one additional thing what we did in xenon anton compared to xenon wonton. So you might be familiar that we had in xenon wonton this excess in our electronic recoil data, which you could account to tritium. And so in xenon anton we took specific measure to exclude this time tritium with higher confidence. So what we did an extensive outgassing and cleaning procedure at the beginning. We were also processing all our xenon through our krypton removal system. So this is also cryptogenic distillation, which also should remove tritium. And then we also did 3 weeks of circulation of gaseous xenon through our hot zirconium getters prior to filling. In addition to that, we did we were operating our detect on a different mode, which we called tritium enhanced mode. In this mode, we were basically bypassing these hot zirconium getters. So you basically get in additional tritium into your detector coming from the systems. However, to estimate how large this enhancement factor is quite difficult. We are confident with saying it is at least a factor of 10, but we have estimated also that it could be very likely to be a factor of 100. But the uncertainties are just so large that this is the confidence we're stating. And when you then observe the data and fit your data, basically what you see is that this data is compatible with the background-only hypothesis, so there was no tritium contamination. So far I showed you basically the data in the mitigating, the calibration data, and the data over here, which is the tritium enhanced and also the calibration data. So let me show you now the data here in between, which is the SR0 science data. So what did we do? We did a blinded analysis below 20 kV. So if you want to say even a double blinded analysis, so we blinded our nuclear recoil data, which is our wind research data, and our electronic recoil data, which is the interesting data from the low ER access. And so what we did, we were first constraining the different background components we expect to see by external measurements, but also by data-driven models. For example, in the case of so-called AC events, which are basically just random pairs of random S1 and random S2 just per chance. And then we did basically stepwise unblinding and verified that these constraints are valid on sidebands basically. So basically you unblind first for higher energies and you try to fit your spectrum, so the counts in versus energy. And what you see here basically is in red the background model and black the data. And so I think the very amazing thing, and I think that's the main message from this talk, is that this shape, if you look at it, it's dominated by second order weak processes. So in Xenon Wonton, we were very happy to see this double electron capture, the KK capture, but now in Xenon Anton you see that it's a very nice peak. We even used it to validate our electronic recoil response models, so that's the degree we know our backgrounds. And what you also can see, we don't only see the KK capture but also the KL capture peak down here. And the other second order weak process is the double neutrino beta decay over here. So now coming to the result. So in Xenon Anton, as I said, we had this low ER access. We also saw it already on Monday. But with Xenon Anton, which is shown down here, basically, we have seen that we don't see any excess. So the excess and Xenon Wonton-like peak excess is excluded by 8.6 sigma. But what you also see is this nice background reduction I was mentioning before of this order factor 5. And if you're more interested in that, you can also refer to this paper on arXiv. So no excess, but what you can still do is computing some limits, a little bit more boring, but still you can do. So if you look at axion-like signals, basically what we can do, we can measure this via the axioelectric effect. And what we basically do is an analysis where we search for or where we can now get exclusion limits on the axion photon and axion electron coupling. And basically you see this is the current result, and this was the confidence limit we gave in Xenon Wonton, so it's basically included. And for iron 56, we also put an upper limit. Then you can also search for other peak-like signals like axion-like particles or dark photon, dark matter, and also here we put some exclusion limit. Not so interesting. And then also for the magnetic neutrino moment, so the enhancement of the magnetic neutrino moment, which you can measure by this electronic recoil data, also just an exclusion limit, but at least if you look at laboratories, that's the most constrained result which we can give so far. So with this, I hope I convinced you that we achieve very excellent background levels and xenon purity in Xenon Anton. So about that, we are very happy. Our subsystems are working very well, even better than expected, partially. And so the ER analysis unfortunately disfavors this Xenon Wonton-like excess. We were able to put new constraints. And so what we're currently working on heavily is the NR unblinding. So our NR data is still blinded down here. We have not looked at this data yet. And we are trying to give you the results also here as soon as possible. And then I think I would also like to close with what we have already also seen yesterday with this unpronounceable thing here, this consortium XLZD. So we're trying now to put forces together from Xenon, LZ, and Darwin to form the next generation of experiments. Also here, please have a look in the white paper. Also see the talk by Teresa about LZ and Adam about Darwin on Wednesday and Friday, respectively. And then thank you very much for your attention.
So, in the past, in 15 kilograms, you did a search and looked for a single electron threshold. And I was wondering if there's a plan to recalibrate and get against single electron threshold. And on the other hand, if there was like you used to cut the highest energy recourse, I was wondering if there's ever a plan to put out data fairly high and fairly low.
Sorry, the second part I didn't catch. The height?
So usually there's a cut on the highest energy recourse that you publish, and we're wondering if there's also a plan for searches with arbitrarily high energies.
Yes, so I mean, you always have to limit these searches. Yes, of course, we're also again looking into these S2 only analysis, as they are called, looking down to single electrons to get also on lower on a lower mass range limits, or maybe find something. Also for the high energy parts, there are analyses underway, but they are not so far yet. But yes, they are still planned.
Sorry, to be more precise, so the Xenon 1 did have an S-only analysis, but I think it had like thresholds like 12 electrons. And the Xenon 15 we also had like 1 electron. I was wondering if that's
so you are sorry, maybe I didn't catch the question. The threshold of what?
Of the number of electrons that you count as an event.
Okay, no. So you mean basically what is the smallest S2 we can basically, maybe this plot is quite nice, the lowest S2s we can measure, right?
Exactly.
And basically you can, with this type of technology, you can measure down to single electron, basically. So this is a log scale plot. A single electron is in the order of 40-ish PE. And so these signals down here would be, for example, or maybe in this cleaned up plot down here would be single electron level. So this is, again, possible, of course, yes.
Thanks for the talk. I just had a quick question.
Can you raise your hand? I don't see you. Here, okay.
I'm just curious, what led you to think that the electrons maybe could have been from tritium?
So we tried to construct, so basically tritium would be in the steel materials, this detector obviously, since it's cryogenic, it has a lot of steel. And it also is contained in air, so basically you have these small amounts of tritium in air. And so what we tried in Xenon 1 ton back then is to give constraints on that, what could be the tritium level. There was always also the other argument that it might be due to argon, basically, this excess. But argon we can constrain a little bit better because we have also this, and maybe also referring to Christopher's poster again, we did this argon calibration in Xenon 1 ton. We have this krypton distillation column, which can also remove argon very nicely. We have proof of that. And also, so this is one of the reasons why we don't think it's argon. So you process the xenon in the very beginning, and so the argon should be gone. If you can still have argon from air leak, but what we calculated, basically you would need an air leak which is that large that you get so many electronegative impurities in your detector that you don't see any S2 anymore. So that's the argument why we don't think it's argon. On the tritium, on the other side, we also try to put constraints, but it's very difficult to estimate how much tritium emanates from all the steel parts. And so that's much more difficult to constrain. And so we cannot repeat Xenon 1 ton, obviously. We cannot go back and check if it's tritium, but our working hypothesis is at least it's tritium. Yeah.
So they're very restrictive then, or the true dipole moment much more restrictive than protein, correct?
Sorry, say again.
The dipole
yeah.
is much more restrictive than that from protein.
Yes. Yes.
So should we also have a very good measurement of the low energy solid flux itself, irrespective of dipole moments?
We hope that we can do that. We haven't done it yet. That's the best answer I can give right now, basically on that.
Thank you very much. Now